Hello, everyone. Welcome to the first set of lectures for CSCI 211. So we're going to start with Chapter 11 in the book, which is Analysis of Algorithms. So I know I said that we're going to primarily talk about data structures in this class, and that's true. But one of the key things that you have to consider when you're choosing your data structure is the performance of the data structure for various tasks that you need to perform. So in order to actually understand the performance, we need to dip our toes a little bit into analysis of algorithms. So if you're a computer science major and you go forward, you're going to be taking a whole class in analysis of algorithms. And a lot of what we talk about in here will be much more formal and much more strictly explained. But we do need to discuss it a bit just so that you have some idea of how these things work, so that when we talk about them, we can talk about the relative performance in different areas of the different data structures. So what we're going to talk about in this chapter, we're going to talk about efficiency goals and the concept of algorithm analysis. We're going to talk about big O notation and the concept of asymptotic complexity. And then we're going to look at comparing various growth functions. So algorithmic efficiency can mean a lot of different things. So usually it's expressed in terms of CPU time. It can also be expressed in terms of memory time or memory usage. It can be expressed in terms of wait time. It can be expressed in terms of lots of things. But in this case, especially for these introductory classes, we're really going to be looking at primarily CPU usage. So the analysis of algorithms involves categorizing an algorithm in terms of efficiency. So we're trying to compare algorithm efficiency. And so we're going to start with a very simple example, which is washing dishes. So let's say that washing a dish takes 30 seconds and drying a dish takes an additional 30 seconds. So therefore, N dishes require N minutes to wash and dry. So in this algorithm, we can see, well, so it takes N minutes, it's 30 seconds to wash, 30 seconds to dry. So for each dish, so that's just N times 30 plus N times 30. So this algorithm is what we would call linear, right? It's a line. So it's linear in terms of N. So as N increases, the amount of time it takes to complete the task increases linearly as a function of N, right? So we're going to look at a slightly less efficient approach. And again, this is just an example, so don't look at this and go, why the hell would you do this? This is just an example. So imagine that we have this less efficient approach and it requires us to re-dry all the previously washed dishes after washing another one. Let's say that we slop water all over the dishes every time we wash a new one, and after we do that, we turn around and go, wow, we have to re-dry all these again. So in this algorithm, we're gonna wash a dish, and then once we wash it, we're gonna re-wash all of the previously washed dishes. Okay, so if you look at the time it takes to wash a dish, let's say the kth dish in our order. So it's gonna take 30 seconds to wash the kth dish, right? Then it's gonna take k times 30 seconds because there's gonna be k dishes already in the rack that have already been washed, right? Or k minus 1. This will be the kth. So we'll put the kth dish in. When we put the kth dish in, we'll have to dry that dish plus the k minus 1 dishes that are already in the rack. And each one of those things takes 30 seconds. So it takes 30 seconds to do the kth dish. It takes k minus 1 times 30 seconds to do the rest of them that are already in the rack. That's a total of k times 30 seconds for the kth dish. So if we're going to do N dishes, we're going to have to sum that up from I equals 1 to N, right? So it's going to take us, for the N dishes, it's going to take us N times 30 seconds to wash because the washing doesn't change. And then to dry, it's going to take us the sum from I is equal to 1 to N of I times 30. So that second term is the drying term. Hopefully that makes sense to you. If it doesn't, you need to look at this again because it's a really crucial kind of thing. You need to think about this because when we talk about loops, there's a lot of cases when we do loops. If you think about loops, the inner loop is a function of the outer loop. Exactly the same thing here. It's not going to be so simple sometimes. In any case, we look at this and we see that this is a summation, and we took calculus. We all took calculus. When you take calculus, one of the things you look at is summations. we know that we can rewrite that summation in this closed form, which is 30n times n plus 1 over 2, right? So it's just 30n times n plus 1 over 2. That's that drying term. And then this 30n is the washing term, all right? If we multiply all that out and we add it up, 30n times n is 30n squared divided by 2 is 15n squared, plus 30n divided by 2 is 15n. So it's 45n plus 15n squared seconds. Okay, so we're in seconds. And that's the amount of time it takes to dry in dishes, or wash and dry in dishes with this new algorithm, right? So the previous algorithm was linear. This algorithm is quadratic, right? Because it's got an n squared term, so it's going to be quadratic. So we can now compare these two algorithms and tell which one is going to be more efficient as we have a lot of dishes to wash. So one thing to note here is that it doesn't matter what happens when n is small, okay? In fact, when n is small, when n is 1, these numbers are exactly the same, right? It's still 30 plus 30 is 1, takes 1 minute to wash one dish. We don't care what happens when n is small, when n is 1 or 2, or even any fixed number. What we really care about is what happens when n gets really, 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 really big. As we let n go to infinity, what happens to these functions, okay? We're not concerned with which one is better for very small numbers of n. We're really concerned with is which one is better when n is enormous, okay? All right, so for every algorithm that we want to analyze, we have to define the size of the problem. So in our dishwashing problem, the size n was the number of dishes to be washed and dried. So if you're doing a search problem, the size of the problem is the size of the search pool. So if you think about this, let's say you've got an array of 100 elements, right? Or n elements. Let's say it's n elements. And you want to find it's unsorted. Let's just say it's unsorted. It's easier to do unsorted, right? So let's say it's unsorted, and we want to say what is the average time to do a search to find a particular, not look it up by its array index, but find, let's say we have 47. 47 is not the array index, it's the value, right? We want to search through this array, which has a bunch of numbers unsorted, and we want to find which array index has 47 in it. Okay, that's our problem. So we're going to have to search. So the way we do that, of course, is we're going to look at the first one. Is it 47? Nope. Look at the second one. Is it 47? Nope. We're going to keep doing that until we find 47 in the array. Okay, that's the default. It's the only thing you can do, basically, if the thing is unsorted, right? So the expected time to find the algorithm in that array would be n over 2, right? Half the time it's in the first half the time it's in the second half. The total is going to be n over 2. So that search algorithm is linear in the size of the array. You're always going to be searching for one thing, but the n in this case is going to be the number of elements that you're searching through, right? So it's different, slightly different. So for a sorting algorithm, the size of the problem is the number of elements to be sorted. So if you're doing a sort, if you're doing a bubble sort or a quick sort, it's the number of things that you have to sort, okay? So we have to define what is the variable that's the problem size. What are we looking at changing? What's increasing? What behavior we're looking at when something... We want to see behavior when something increases. What is the thing that's going to be increasing? Basically, is what we're looking at. So search algorithms is the size of the pool. For sorting algorithms, it's the number of things that you want to sort. All right. So for the other thing that we need to look at is the growth function. What are we trying to efficiently optimize? So we could look at different things, actually. We could look at time complexity, which is how much CPU time it takes to solve a problem. We could look at space complexity, which is how much memory space it requires for us to solve a problem. And if you get into more advanced algorithms, you see that there's actually a time, what they call the time-space complexity trade-off, where we can oftentimes decrease the time complexity by increasing the space complexity, or decrease the space complexity by increasing the time complexity. And exactly which one of these you're looking at is going to depend on what you're looking at. I mean, it's going to depend on the problem that you're looking at. So if you're looking for like enormous, like your Google, and you're looking at images, like there's no way that you could store every single image that Google owns in a memory. Like, no matter how big the machine is, they're just not all going to fit, right? In that case, there's some trade-off. You've got to, what's the most efficient algorithm with respect to CPU time, given some memory constraint. So there's a space complexity constraint. And then we want to find the best time complexity solution to that problem. But in the beginning of these things, we're first just talking about these little data structures and stuff that you guys are going to be looking at. We're really just going to be mostly looking at CPU time. And when you go and take databases and some of these other classes, some of these other things will matter. But right now, we're just going to look at CPU time for the most part. All right. So the growth function shows the relationship between the size of the problem n and the value that you're trying to optimize. So in this case, it would be time. So the growth function is, as n grows larger, how does the time grow? The time to solve the problem grow. So we have this concept of asymptotic complexity. So the growth function, for example, in that second dishwashing algorithm is 15n squared plus 45n. So if you think about it, in terms of dishwashing, let's just use our dishwashing analogy. Like they said it took 30 seconds, right? But that is somebody who's pretty slow at washing and drying dishes. Let's say I can dry them faster at 10, right? So what's going to change in that case is going to be those coefficients, right? That 45 and that 15 are going to change, but that n squared and that n are not going to change, right? And if I went back to the first algorithm, which is just 60n, if I can do it in 10, that becomes 20n. But the fact that that's 20n really doesn't have any impact. That 20, that constant, has no impact in deciding which one of these algorithms is better, right? Because as n grows large, irregardless of which one of these constants is there, it's 15, it's 30, it's 20, whatever it is, the complexity of the function is going to increase quadratically in this case and linearly in the other one. And eventually the quadratic one is going to be more costly than the linear one, right? It doesn't matter what the constants are. It's still going to be... So in some sense, we're not really concerned what the constants are. So what we're mainly interested in is sort of what does it look like? What's the shape of it as it grows? The general nature of the algorithm is incomplete, increases, not the exact value of it. Because there's a lot of variables in that, right? There's the CPU time or CPU speed. There's the amount of cache. There's the speed of the memory, the size of the memory. There's a lot of different factors that what programming language we used, how the compiler optimizes. There's a lot of different factors that are going to affect those constants. We don't really care about those. What we really care about is the asymptotic complexity. So how does it grow over time when we're picking these algorithms? So asymptotic complexity is based on the dominant term of the growth function, the term that increases the most quickly as n increases. So before I said the constant terms don't matter. The constants don't actually matter. It turns out that actually even the linear term, the n term, doesn't really matter at all anyway. So you look at this chart. We can prove this later on when we more formally define this, and we're not going to do that. It's going to be in algorithms. But if you look at this chart, you can get a feel for this. So there's the 15n squared, and we look at it, and actually in the beginning, it's actually smaller than the 45n component, right? The 15n squared component. And then actually even for 2, n equals 2, it's still smaller. But remember, we don't care what happens for small numbers. Small numbers don't matter to us at all, okay? We only care about what happens when things get really, 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 really big. So let's kind of look at the trend here of what happens. So look at the 15n squared term when we get up to 10 million. It's an enormous number, right? 45n is much, much smaller than the 45n term at 10 million is much, much smaller than the 15n term. And eventually, if we keep doing this, the 45n term will turn into round-off error, right? We won't even notice it if we take it out or not. And that's sort of the gist of this, is the idea that the n term doesn't matter at all. The dominant term in this is the n squared. If we let n get big enough, that 45n, we might as well just make it 0. We're not even going to notice if we clip it off. It's just going to be like 0. So that's into the first section of this lecture. Come back for the second section. Thanks.